All right. Good morning again, Chazelle, Christine, Denmark, Nariel, and Nerissa. Before we proceed, Chazelle would like to announce something. Sige, Chazelle, kahit lilima pa yung estudyante, makikita naman nila sa recording. Go ahead.
Thank you po. Good morning, everyone. I am Chazalinis Casanova, and on behalf of AMAT 199 Section T, under the supervision of Associate Professor Aleli Domingo, I would like to invite all of you to our upcoming webinar event with the theme Past, Present, and Future, the Old Script Meets the New Technology. This webinar will happen on Monday, 15th of November 2021, 9 o'clock a.m. via Zoom and Facebook Live. Our guest speaker, Mr. Rodney Pino from the University of Philippines Diliman and Baguio, will discuss their study entitled Optical Character Recognition System for Bayesian Scripts using Support Vector Machine. If you are interested, you can pre-register using the link you can find on our Facebook page. Certificates of participation will be distributed to the participants if they answer the evaluation form. Also, Sir Neil mentioned that he will be giving incentives if you attend the webinar and also pass the necessary requirements he will require. For more updates, you can check our official Facebook page, AMAT199-seminars. If you have other concerns, you can also send us a message on our Facebook page or send us an email at amat199.externals@gmail.com or amat199.records@gmail.com. Thank you so much, and together let us unveil the relationship of the past, present, and future. Thank you po, sir.
All right. You're welcome, Chazelle. All right. So, for those who are interested or have nothing better to do on Monday, so you guys can check out and attend the AMAT 199 seminar if your schedule allows it. And I'll be giving little incentives for those who will be attending the webinar. I would just like to require you with, say, a reaction paper, a couple of paragraphs, or a couple of pages long. Bahala na kayo. Sulat lang kayo or i-type nyo lang or sulat kayo ng something to describe what you get from the seminar. What's your opinion about it or anything? Just give me something to give you a grade on. I'll open up a submission bin in Canvas for the reaction papers where you guys can submit your work. Okay. So yeah. So if you're interested, then join the webinar. All right. So thank you, Chazelle. Do we have some housekeeping matters? May announcements ba dapat? Mukhang wala naman. We can now proceed with the actual discussion. Last time we talked about improving numerical differentiation formulas, which we obtained using Taylor's theorem, which resulted into what we call a finite difference formula. So, ang ginawa natin ay binalance natin yung pagpili ng step size. Theoretically, when we derived the method, we said that the methods that we are considering have accuracy that depends on the power of the step size h, right? So, halimbawa, yung three-point centered formula of order 2 ay nagko-converge dun sa actual derivative as fast as how h squared approaches 0. So, theoretically, when we drive h closer and closer to 0, dapat yung error lumiliit ng lumiliit. But to our surprise last time, ginawa natin tong experiment na to with a simple differentiation formula for e to the power x at x equals 0. And we have noticed that after some point, nag-underperform na yung method dun sa theoretical order of convergence. So siguro sa mga 10 to the negative 1, 10 to the negative 2, 10 to the negative 3 na step size, I think up to 10 to the minus 10 to the minus 8 or something like that. Nakikita natin yung pagbaba ng error at the same rate as h squared, right? Nadi-divide by 100 yung error habang dinidivide natin yung step size by 10. And that is what we expected. But after some point, pag masyado nang maliit yung h, medyo nag-underperform na siya. Hindi niya na na-attain yung order of convergence h squared. And um, up to some worst cases, lagi na masyado nang hindi ganon kagandahan yung approximate. Remember, where we have a case wherein we have a very small step size and we have relative error of about 45%. So, ibig sabihin, we have to strike a clear balance between the value of h. It should not be too large para mababa yung theoretical error, and it shouldn't be very small so as to allow the propagation of round-off errors. Kasi nga, pag in-implement natin yung method sa isang machine, nagta-truncate siya ng significant digits after every operation. So pag sobrang liit na nung differences dun sa numerator, medyo in-evaluate niya to be equal to zero, then magfe-fail na yung method. So yung near optimal step size na nakuha natin last time strikes the balance between the theoretical error and the round-off error due to machine implementations. So last time, the improvement that we talked about is more on the local side, wherein we look at the best H or the near best H for to or with respect to the theoretical and the round-off error. So for today, we will look at a more, we can say global improvement of the method in the sense na gagamit tayo ng iba't ibang H's. Tapos itatry nating pabilisin yung order of convergence. So in the three-point centered formula of order 2 that we tackled last time, sabi nga natin, kasing bilis ni h squared nagzi-zero yung error. Okay? Pero kapag gusto nating pabilisin yung order of convergence, ibig sabihin we want to find a formula that will converge to the actual derivative value faster than h squared. So medyo papabilisin natin yung convergence. And the process that you will see today will actually involve several iterations of the method. Kailangan nating i-perform yung basic numerical differentiation formula na na-derive natin sa iba't ibang value ni h at gamitin yung mga approximates na yon o nung sequence ng approximates na yon to get another sequence of approximations that will converge faster to the actual value. So before we go there, let's probably have a quick recap of the big O notations, okay? Now, tatandaan nyo, we said that a function g, say of the variable h, is a big O of h to the k if in the long run, g of h or the magnitude of g of h is bounded above by a multiple of h to the power k. Alright? So yan yung ibig sabihin or yan yung definition ng Bachmann-Landau notation na big O ni h to the k. So in the long run, uh, as a multiple of h to the k will serve as an upper bound for the magnitude of g of h. So kaya nga ang tawag natin kay h to the k ay isang asymptotic upper bound para kay g of h. Alright? It's either, or kung babalikan natin kasi dito medyo infinitesimal yung tinitingnan natin. Infinitesimal case meaning h's go to zero kasi nga yung h yung ini-interpret natin to be the step size and usually we want the step sizes to be closer to zero, right? So an equivalent definition to this for the big O notation, but dapat sigurado kayo infinitesimal kasi may dalawang big O notation. Isa sa infinitesimal at saka isa sa infinite case. So it's either h going to infinity or h going to zero. Ang tinitingnan natin ay infinitesimal sense. So si h papunta kay zero. So the corresponding alternative definition for this Bachmann-Landau notation ay ito. Pag kinuha mo daw yung limit ni g of h all over h to the k o yung absolute value ng ratio na to, as h approaches zero, kasi nga infinitesimal sense tayo, dapat siya ay bounded by a constant c. Alright? So that's the requirement para magtawag natin na big O ni h to the k si g of h. Or the other way around, big O ni g of h si h to the k. Right? But how do we interpret this, guys? Ano yung pwede nating sabihin kapag yung limit ni gh all over h to the k as h approaches zero ay bounded above by a constant? So what can we say about g and h to the k? How do they compare with each other? Any idea? Abang higup lang ako ng kape. Ano yung ibig sabihin nun? Kapag yung g of h over hk as h approaches 0 ay mababound ng isang constant. Kung naalala niyo yung interpretation ng limit sa Math 36. Anyone? Ito, bonus points. Maliliit na bonus points for the problem sets. Anyone who wants to try? Okay, may mag-try. Wala naman deduction kapag kamali. Sige kayo, magtatawag ako. Pero Zoom sa kaanaw ng Teams. Tas bawal gamitin yung pinagbabawal na technique na kunwari na disconnect. Sige, let's try Alex or Alexandria. Ano yung posibleng interpretation kapag yung limit ay bounded above by a constant or equal sa isang constant? Any guess? All right, no guess for now. So, kapag ang limit ng g of h over h to the k ay bounded above by a constant, ibig sabihin, roughly, g and h to the k are proportional to each other or magkasing bilas sila ng rate of growth. All right? So, ibig sabihin, kapag totoo itong limit statement na to, bounded above by a constant, ibig sabihin, g of h and h to the k experience the same growth rate as h approaches 0. Halos sabay silang lumalaki or lumiliit, or actually, magkasing bilis silang lumiit habang lumiliit si h. Alright? Kasi nga near proportional sila. Yung ratio between them is almost a constant. So we can say they are almost proportional to each other, meaning they will grow at the same rate. Okay? And this is what we said. Ito yung big O talaga. Ito yung interpretation natin ng big O. Kaya pwede natin talaga sabihin na magkasing bilis yung behavior ng paglaki or pagliit ni g of h at saka ni h to the k up to some multiplicative constant. Alright? Now, if it happens that the limit of the ratio is equal to 0, then we say that g of h is a small o or is a little o of h to the k. All right? So pag in-evaluate nyo itong limit na to, naging equal siya kay 0, then that's the time that g of h is a small o of h to the k. Now, how do we interpret this? Anyone who wants to try? Ano naman yung interpretation nito? Okay, no volunteers then. All right, so the interpretation here is nagsizero ang ratio kapag yung denominator ay mas mabilis ang paglaki kesa kay g of h. All right? So that means the denominator beats the numerator in a magnitude contest, kaya yung limit nag-approach ng 0. All right? So mas mabilis yung paglaki ng denominator kesa sa numerator, such that in the long run, as h approaches 0, yung ratio ni g of h all over h to the k ay nagsi-zero. So, ibig sabihin, mas mabilis yung paglaki ni h to the k kesa kay g of h. Or alternatively, mas mabilis yung pagliit ni g of h kesa sa pagliit ni h to the k. Because h to the k remains or becomes significantly larger than g of h as h approaches 0. And with this in mind, it seems that we like or we want methods that are little o of h to the k rather than methods that are big O of h to the k. Kasi ang interpretation nila, kapag meron kang formula na big O of h to the k, yung error ay nagze-zero kasing bilis ng pagze-zero ni h to the power k. Pero pag meron tayong formula na little o of h to the k, mas mabilis nagze-zero yung error kesa sa pagze-zero ni h to the power k. Alright? And that's our goal for this section, for the Richardson Extrapolation section. Gusto nating i-improve yung method natin na big O of h to the k at itaas yung rate of convergence niya to a little o of h to the k. Right? Now, how will we do that? Well, we'll take advantage of this guy. We want to force the issue that the limit of the ratio between yung g of h, papalitan ko lang ng error term. Okay? Gusto ko yung limit ng absolute value ng error term over h to the power k, where h to the k is the known order of convergence of our method. Gusto kong i-force yung issue na yung limit na yan ay magzizero. Kasi pag nagkataon, yung order big O of h to the k magiging order little o of h to the k na lamang. Right? Now, just to summarize this, okay, meron ako ditong dalawang bullets para mas madali nyong ma-review. Kapag ka meron tayong formula, for instance, d yung actual derivative, and we approximate d using an approximation formula that depends on h. So si d, siya yung actual value ng derivative. Si d of h, ito yung approximation na nakuha natin using the finite difference formula that we have derived with step size h. Tapos kung ang error term niya ay big O of h to the k, ibig sabihin nagko-converge yung sequence of approximations obtained by various step size h papunta dun sa actual value kasing bilis ng pagzizero ni h to the power k. Alright? And we already know this from last time. Now, what we have just discussed is the case wherein we have an approximation formula d of h that converges with order little o of h to the k. This means that the sequence of approximations we obtain with varying step sizes h will approach the actual derivative faster than how h to the k approaches 0. Okay? So yun yung gagawin natin dito. And this process is called the Richardson Extrapolation. We will speed up the convergence, not by one order, pero konting-konti lang. Kasi ayaw natin gawing mas komplikado yung computation. So the idea here is, instead of getting a formula that is big O of h to the k, we will translate it into a formula of order little o of h to the k. All right? So to illustrate this process, I'm going to use the 3-point centered formula of order 2 na pinaglaruan natin last time. Ito na rin yung gagamitin ko, but the process and the extension will be the same para dun sa ibang mga formulas. So please keep attention to what I'll be doing here. Make sure you understand the process because in the lab exercise on Monday, you will be asked to perform Richardson extrapolation, derive the actual formula for another numerical differentiation formula. So ipapakita ko kung paano siya gagawin dito sa specific formula na to, and you'll have to recreate this for a different differentiation formula. Okay? Maybe we can talk more about the lab exer later, but let's go here. Okay? So recall this is the 3-point centered formula of order 2. Ito yung ginagamit natin na pang-differentiate. All right? So pang-approximate sa derivative. And then the error term is minus h squared f triple prime of c, where c is a number between x minus h and x plus h. Maybe we should highlight that here. C is an unknown number from x minus h to x plus h. Right? Kaya hindi natin eksaktong mako-compute yung error. Kasi hindi natin alam posible yung third derivative, hindi rin natin alam yung number c na kailangan kong i-plug in dun sa third derivative. Now, we already know that this is a big O, or this formula is a big O of h squared. And let's try to check it via the definition, okay? So we let d to be the actual derivative and d of h be this guy. So ito yung tatawagin nating d of h. Kasi ito yung approximate natin para dun sa derivative pag ginamit ko yung step size h, alright? So ito si d of h. So sabi nung alternative definition natin sa big O, pag kinuha daw natin yung limit nung error term, so yung error term ay d minus d of h, actual minus approximate, all over h to the power k. We know our formula is of order big O of h to the second power. So i-divide ko siya by h squared. And what I expect is to get a constant, all right? Now, we already know that d minus d of h will be this guy, all right? It would be negative h squared over 6f triple prime of c. Ito kasi yung error term, right? Tapos i-divide ko siya by h squared, maka-cancel si h squared, matitira lang sa atin ay ito. And this guy is devoid of h, wala na siyang h, so ito na yung final answer natin sa limit. Okay? But another form, instead of the unknown number c, kasi problematic yung paggamit ng number c kasi hindi natin alam kung ano talaga yung value ni c. Ang alam ko lamang, si c ay isang number mula sa x minus h hanggang x plus h. So to remove c from this equation, pwede kong gamitin yung knowledge na si h ay nag-approach ng 0. We're doing a limit as h approaches 0. Ano yung mangyayari kapag si h ay palapit ng palapit kay 0? Yung x minus h at saka x plus h palapit ng palapit dun sa center ng neighborhood, palapit sila ng palapit kay x as h approaches 0. Alright? Kasi pag lumiliit yung increment, etong dalawang bounds na to ay palapit ng palapit kay x. So eventually, I can replace c by the variable x na lamang. Alright? Kasi nga, you can think of this as an open interval. Tapos kapag si h ay lumiliit, yung interval lumiliit, as h becomes 0, isa na lang yung natitira dun sa interval. Si x na lang yung natitira dun sa interval. Alright? So that's why we can say it's a 1/6 or the absolute value of 1/6 f triple prime of x. And usually x is the number at which we would like to evaluate or approximate the derivative at. All right? Is it good so far? Reacts naman kayo dyan kung okay pa. Are you with me? Or busy kayo pag-almusal? Okay, thank you guys. All right, so again, we already know this, pero binerify lang natin na yung formula natin ay order big O ni h squared. And now, as I have promised, we will develop a technique on how to speed up the convergence from a big O to a little o of h squared. Okay? Tapos ano nga yung requirement? Nagkakaroon tayo ng little o kapag yung limit na to ay hindi lang bounded by a constant, pero gusto ko yung limit maging eksaktong 0. All right? So I want the limit of this guy, okay, but the numerator would be an error term, right? Yung numerator magiging error term. Yung limit ng error term over h squared, gusto ko mag-0. Pag wala tayong ginawang pagbabago dun sa formula natin, alright, ang limit ay magiging 1/6 f triple prime. Medyo dadayain ko siya ng konti. Mag-0 yung limit, or one way to make the limit equal to 0 ay gawin kong 0 yung numerator. Or I'll force the issue that the limit of the numerator will go to 0. Alright? So yun yung gagawin kong pandaraya rito. So alam natin na yung d minus d of h ay equal dito, yung error term. So what I'll do, the trick here is i-add ko yung negative nito, pero palitan ko si c ng x. Kasi alam ko, in the long run, yung limit ay magiging 1/6 f triple prime of x. So kung yung limit, yung original limit, babawasan ko yung numerator niya by this guy times h squared, mafo-force ko na magze-0 yung numerator. So tingnan nyo lang yung error term. Tapos, idagdag nyo yung opposite sign niya dun sa numerator. So I have a minus h squared over 6 f triple prime of c. Papalitan ko yung numerator dahil negative yan. Laplasan ko siya ng same thing, pero yung c papalitan ko ng x. Ina-avoid ko yung paggamit ng c as much as possible kasi unknown number yon. Pero remember again, the trick is we're taking the limit as h approaches 0. So si c pwede kong palitan ng x. Kasi si c naninirahan siya sa open interval x minus h, comma x plus h. Habang lumiliit si h, si c nafo-force to be very, very close to x. All right? And that's what I did here. Okay? So eto na yung target ko na maging error formula. Yung sa bagong or yung error term para sa bagong differentiation formula natin. Okay? Medyo baligtad. Nag-contrive yung process. minanipula ko yung error term para yung limit niya over h squared ay mag-approach ng 0 para masabi na little o siya. So pabaliktad yung ginawa ko ngayon. Alam ko yung gusto kong maging error term. Right? Tapos mula dito, saka natin i-derive yung differentiation formula. Alright? And let's just double check and see really that this will work. If we will evaluate the limit, so yung numerator d minus dh over h squared over 6 f triple prime of x, magiging equal siya sa um, negative h squared f triple prime of c plus h squared f triple prime of x, right? Pag sinimplify ko yung numerator, tapos i-divide ko sila by h squared. So makakancel yung mga h squared. Matitira lamang ay ito. Okay? 1/6 ng f triple prime of x minus f triple prime ng c. Pero we are taking h to 0. Alright? And again, habang palapit ng palapit si h kay 0, si x or si c palapit ng palapit kay x. So eventually, in the limit, this guy will become 1/6 times f triple prime of x minus f triple prime of x, and that is equal to 0 as we have desired. Okay? Now that means any formula whose error term will look like this will be of order little o of h squared. So in the formal language that we have introduced earlier, if this the actual derivative, then if this guy will serve as the actual error, okay? Ibig sabihin yung d ay magiging equal sa d of h plus k1h squared, right? Plus little o of h squared, where k1 is negative 1/6 f triple prime of x. Okay? So ito yung error term, diba? Ito yung sabi natin gusto nating error term. Eh, ang formula ng error term ay actual minus approximate. Okay? So ito yung actual value. Ito yung actual value. So whatever the subtrahend is, yan dapat yung approximate natin. Alright? So ito yung approximate natin. Yung bago nating approximation to the derivative would be d of h minus h squared over 6 f triple prime of x. Alright? Kasi i-group ko to sa isang grouping symbol, pero ito magiging negative para pag dinistribute ko siya, makukuha ko yung desired numerator. Alright? So basically, this would be our new differentiation formula. Kaya nakuha siya dito. Alright? So yung f triple prime of x over 6, pinalitan ko siya ng k1. I just used the placeholder k1 of h squared. And since we have this limit, approach being equal to 0, siya ay little o ni h squared, right? So now we have this new formula, this new approximation formula that will converge faster to the actual value than h squared. So mas mabilis siya dun sa original formula na kinonsider natin. Kaya lang medyo may konting problema to. Anong problema rito? Para magamit itong formula na to, kailangan niya yung f triple prime of x kasi may k1 tayo dito. Si k1, ang value niya ay negative 1/6 ng f triple prime of x. So that means we have to pay the price for increasing the order of convergence. Kailangan gamitin ko or magkaroon ako ng data para kay f triple prime of x, which might not be possible kasi ina-assume natin sa paggamit ng numerical differentiation formula, ang data lang natin ay x at saka f of x or mga x's at yung mga function values nila. So it doesn't make sense to rely on having access to f triple prime. At saka medyo kakaiba yung kaso na yun pag may access ka sa f triple prime. Ina-approximate nga natin si f prime. So ibig sabihin, di natin kayang computein si f prime manually. So the more that it would be difficult to compute f triple prime. So it is fair to assume that we don't have access to this data. So itatapon na lang ba natin tong formula na to? Hindi. Kasi mga mathematicians tayo, medyo um, magaling tayong mandaya sa mga formulas. So ito yung method kung paano natin matatanggal si K1 from the equation. Alright? So how can I replace K1 by another formula or another expression or value that we have access to? Alright? So ang idea ay ito. Alright? So I just copy the formula over here. And then, eto yung sacrifice na gagawin ko. Ayoko kasing, alam ko na wala akong access sa data na yan. So, ang gagawin ko, hanap ako ng alternative. At ang isa-sacrifice ko ay yung paggamit or pagra-run ng isa pang instance noong basic numerical differentiation formula, but this time with a different step size. A step size that is proportional to the original step size h. So kung ito yung approximation, pag ginamit ko si step size h, what I'll do is I'll rerun the algorithm, but this time using half the original step size. So mangyayari, mula sa formula na ito, lahat ng h papalitan ko ng h over 2. So instead of getting an approximate using step size h, we can get an approximation using step size h over 2. Now, medyo arbitrary yung pagpili ng bagong step size. You could have chosen replacing this by h over 3 or h over 4. Pwede nang palitan nyo siya ng h over 10, h over 100, and so on. That's fine. Pero I'll be more conservative here kasi sabi nga natin baka yung mga methods natin ay mas mabilis ay actually kapag i-implement ko siya sa computer, pag masyado kong binabaan yung step size, posible na maging significant yung round off error. So ayokong masyadong mabilis pababain si H kasi baka ma-hit ko yung tolerance nung computing software na gagamitin ko when it comes to significant digits. So ayokong masyadong babaan si h. So that's why the conservative choice is to replace h by h over 2 para pa konti-konti lamang yung pagliit ni h pag inimplement ko siya sa computer. Alright? So I just replace h here by h over 2. And then ito si h dito mapapalitan din ng h over 2. So magkakaroon ka ng h over 2 squared. That's how we get K1. That's a constant that doesn't depend on H times H squared over 4. Tapos, dito sa little o, magiging little o siya ng H squared over 4. Alright? Pero remember sa Bachman-Landau notations, we always drop the constant multipliers. So yung 1/4 na multiplier dito, I can just get rid of that. Little o of h squared over 4 is still a little o of h squared. So yun yung kagandahan sa Bachman-Landau notations. Hindi natin kailangang i-keep track yung mga constant multipliers at saka insignificant addends. All right? And then what I'll do next is to subtract the second or the corresponding sides of the second equation from the corresponding sides of the first equation. So we'll have d minus d, that's going to be 0, d of h minus d of h over 2, k1 h squared minus k1 h squared over 4. You're going to get 3/4 of k1 h squared. Tapos big O of h, little o of h squared plus little o of h squared, that will still be a little o of h squared. If you forgot the Bachman-Landau, the arithmetic on Bachman-Landau notations, you can check out the worktext. Meron dong isang section sa Bachman-Landau. So meron dong list of theorems para sa pag-perform ng arithmetic on them. But believe me that little o of h squared plus little o of h squared is still a little o of h squared. Right? Or kahit minus pa siya. Little o minus little o, parehas yung argument. So, mariretain yung isa sa kanilang dalawa. Okay? And then from here, I can compute for K1. Alright? Yun pala, in-eliminate ko si D kasi wala naman akong access kay D. Si D yung actual derivative. So I don't want it to be in the resulting equation. So tatanggalin ko siya. Kaya in-eliminate ko si D. And luckily, if you look at the equation, all that remains here na unknown ay si K1. Sa lahat ng expressions dito, si K1 lang yung wala tayong access. So ngayon, kaya kong isolve itong equation na to for K1 in terms of D of H and d of h over 2. And true enough, k1h squared is equal to this guy. Right? Ang kagandahan dito ay ito yung pang-approximate ko kay k1h squared and we have access to d of h. Ito yung estimate natin using the formula with step size h. Ito yung approximate natin using the formula but with step size h over 2. So we can easily compute these two guys. Sila yung pampalit kay k1h squared. So if you go back to this formula, okay, balik tayo dito sa actual formula na supposedly gagamitin na sana natin. Kaya lang nagka-problema tayo kay K1 kasi hindi natin alam si K1. But now we know saan equals si K1. So pwede kong i-plug in itong equation, itong expression na to para kay K1H squared dito sa formula na ito. So we'll have D is equal to D of H plus K1 of H squared is 4/3 ng D of H over 2 minus d of h, tapos plus little o of h squared, plus little o of h squared, little o pa rin siya ng h squared. Okay? And then if we simplify these two terms or combine like terms in these two terms here, we'll get this final formula. Okay? So para pala magkaroon tayo ng formula na yung pag-converge ng sequence of new approximates ay mas mabilis sa pag-zero ni h squared, kailangan ko lang gawin itong simple linear process para sa dalawang magkasunod na approximates. Alright? And it seems that the price we need to pay to speed up the convergence is not that expensive kasi kailangan ko lang dalawang magkasunod na approximate. Computin ko ito, i-divide ko by 3. That's easy to perform. Mas mabilis na yung convergence ng formula. All right? So I hope the derivation made sense. Any questions before we see a machine implementation of this in Excel? Clear pa naman lahat? Okay. Sana naintindihan niyo yung process kasi sa lab exer kailangan yung gawin ito pero iba yung formula. Actually hindi pala. Medyo sinuwerte kayo dun sa lab exer. I'll mention some things about that later. Pero another thing about this formula is that hindi pala necessary na siya ay gamitin para sa isang differentiation formula. Because in the derivation that we have encountered here, okay, kinip lang natin yung d of h over 2 at saka yung d of h. And except for the fact that pinili natin yung gusto nating error term para mag-zero yung numerator, si d of h ay walang kinalaman or hindi kailangan magkaroon ng something to do with the numerical differentiation formula. So actually, this guy can be used to speed up the acceleration of any method of order big O of h squared. So halimbawa, meron kayong formula na ginagamit sa SP nyo, isang optimization problem or isang optimization algorithm that converges with order big O of h squared. Kung nababagalan kayo sa pag-converge ng method nyo, pwede nyo pabilisin yung order of convergence using this same formula. As long as alam nyo na yung method na ginagamit nyo ay of order big O of h squared. So yung makukuha nyo out of this new formula will converge a lot faster. Or a little faster. Hindi pala a lot. A little faster lang. Okay? So ibig sabihin si d of h, hindi siya necessarily equal dito sa 3-point centered formula. Okay? So posibleng ibang formula si d of h kahit hindi siya numerical differentiation formula. Pwede siyang root finding technique. Pwede siyang optimization technique na order big O of h squared. Pero ang problema, kapag hindi nyo na ito pwedeng gamitin kapag iba yung order of convergence. Pag yung original formula nyo na d of h ay order, say, big O of h cubed, kailangan yung ulitin yung derivation na ginawa natin, tas posibleng iba yung makuha nyo na formula para sa pag-speed up at maitaas yung order of convergence to little o of h cubed. All right? So with that in mind, let's look at an implementation of this method. So gamitin natin itong 3-point centered formula. We know this is of order 2. And then let's speed up the approximation of the derivative of e to the x at x equals 0 using Richardson extrapolation. Okay. So I'll do this again in an Excel spreadsheet. So okay, so I hope you guys can see my Excel screen. Let me know kung masyadong maliit yung font. I hope it's fine. Okay, so magsimula tayo sa h ay 0.1. And then 3-point yung 3C2, ibig sabihin 3-point centered formula of order 2. Ito yung approximation na makukuha natin. So ina-approximate natin yung derivative ni e to the x. So ang f of x natin ay e to the x. So it's gonna be e to the 0 plus h minus e to the 0 minus h divided by 2 times h. Right? Ba't siya nagreklamo? Okay. Kulang yung mali yung placement ko ng parentheses. Nangyari. Saan ako nagsobra ng okay. Hindi ko pala na-close yung parentheses dito. Yun nga lang yung problema, no? Pag maraming grouping symbols. Yeah, I think this is right. Double check natin. E to the 0 minus e to the 0 minus h. Difference divided by 2 times h. Okay. And then compute natin yung error. So we know the exact value, luckily. So the actual value is 1. So we'll have the approximate minus 1. Kunin natin yung absolute value. Yeah, this is the error we got last time. 1.67 times 10 to the minus 3. And then what we'll do is to take half of the original step size for the next iteration. So divide ko yung step size natin kanina by 2. So now the step size is 0.05. So drag ko lang yung formula para makuha ko yung bagong approximate. Tapos tingnan natin yung error. So yung error, bumaba siya to 4.2 times 10 to the minus 4. And let's see if that is as expected. By what factor dapat ma-divide yung error? Ang error, ang ating method ay order big O of h squared. Yung step size, dinivide ko by 2. So yung error dapat ma-divide by 4, right? So let's see if that happened. Tingnan natin yung error. Divided by the next error, dapat around 4. And there we go. Really, it's about 4. And that is expected, again, because we divided h here by 2. Ang formula natin ay big O of h squared. So ibig sabihin yung error dapat ma-divide by 4. Right? Then let's continue the process. Okay. And then computing ko rin yung relative error. And then tingnan ko yung ratio just to verify the convergence. And then here you see that indeed around 4 lagi yung quotient between two consecutive errors kasi nga yung step size patuloy nating dinidivide by 2. So everything is well here. Tapos yung approximation natin after how many? After 14 iterations, ang error na nakuha na natin ay down to 2.2 times 10 to the negative 11. So it took 14 iterations to bring the error down to that level. All right? Pero gamitan natin siya ng Richardson Extrapolation. Okay? So kung babalikan nyo yung bagong formula using the Richardson Extrapolation, ay ganito daw yung gagawin natin. 4 times the estimate using half the step size. So ito yung nasa formula sa numerator ng formula kanina na 4 times d of h over 2. So yung approximation natin using step size h over 2, so siya yung nasa cell B5, minus the approximate using step size h divided by 3, right? Tas ito yung bago nating estimate. And if you compute the absolute error, so that would be estimate minus actual value, you see the very big difference or the very big improvement in the relative error. So yung relative error kanina, 1.67 times 10 to the minus 3, that's one calculation. Tapos ngayon, sa unang term pa lang, ng sequence of approximates using Richardson extrapolation, 10 to the negative 7 na kaagad yung error. Alright? So, kung bibilangin mo yung parang computations na ginawa natin, how many big chunks of calculations did we do? So, kinompute natin to isa, tapos kinompute natin yung D of 0.5 dalawa, tapos nag-Richardson extrapolation ako tatlo. So, pwede mong isipin, tatlong beses akong gumawa ng big calculations. Yung error ay 2.03 times 10 to the negative 7. Pero pag tatlong basic numerical differentiation formula lang yung pinerform ko, tingnan niyo yung error dito sa pangatlo. Ang error ay 1, 2, 3, 4. 10 to the negative 4 pa lamang. So really, mas maganda yung nakuha ko sa Richardson extrapolation. Okay? With around the same amount of effort or computational effort. Okay? Now I'll drag this formula down. And then let's see the relative error or the absolute error. Okay. And you will see na, okay, medyo nag-underperform na siya dito, possibly due to machine precision, all right? Pero tingnan nyo, yung pinakamaganda sa basic numerical differentiation formula na nakuha natin, 2.2 times 10 to the negative 11 yung error, pero tingnan nyo dito, dun pa lang sa Richardson extrapolation dito, umabot na siya ng 3.2 times 10 to the negative 12. All right? So mas kakaunti yung number of iterations required using Richardson extrapolation. At saka kung makikita nyo dito sa chart sa kanan, yung blue line siya yung error sa 3-point centered formula. It looks linear kasi parang nadi-divide lang siya by 4, tama? Pero mas mabilis yung pagbaba ng error lagi para doon sa Richardson extrapolation. Okay? Pag kinuha natin yung ratio between two consecutive errors kay Richardson, okay, ito pala yung bago, yung luma over the bago. Kanina na-divide lang by a factor of 4. Ngayon na-divide siya by factor of 16, 16, 16, 15, 21, 10. So mas mabilis yung pagbaba ng error kesa sa pag-zero ni h squared. Except dito sa line na to, kasi makikita nyo yung improvement dun sa errors ay hindi na ganun ka significant. So pwedeng sabihin mo, okay, since I am not getting significant improvements by carrying out additional computations, I will stop probably here. At ito na yung i-consider kong best approximate for the best estimate for the derivative. Okay? So yun yung gagamitin ko kasi hanggang dun lang ako nakakuha ng significant improvement dun sa error. Alright? So we'll live with this and the absolute error here is 10 to the minus 13. Remember, si Excel nagkikeep lang ng 15 significant digits. So napakalapit na nito sa machine precision. So this is almost the best that we can get out of Excel. Or 1.42 times 10 to the negative 14. That's the best that we can get. Or near the best that we can get. Okay. Now, any questions with the Excel implementation? I hope you appreciate how Richardson extrapolation indeed sped up the conversion of our the convergence of the sequence of approximations that we get to the actual value. All right. So, mabilis, sorry, na overtime na naman ako. Puntahan natin yung lab exer, mabilis lang, so that you'll have an idea of how to proceed with that. Okay. Now, ang coverage ng XOR 4 ay Module 6 and 7. So first instruction, derive a 4-point backward formula of order 2. Wala na yung both. So isa lang yung i-derive nyo. Tapos of order 2 dapat. So I hope you remember how to do that. So if not, go back to module 6, right? And then we will implement this 4-point backward formula para sa model, para sa population ng United States that was modeled using data from 1790, 1850, and 1910. Okay? So ito yung model daw para sa population ng United States where T is the paki-verify na lang. Sabi nung lab instructor na sumulat nung XOR, T is the year, is the actual year. So paki-verify na lang pagka medyo ambiguous yung yung model o yung data. So pwede niyo siyang i-verify using actual data. So sabi rito, itong model daw na to ay nanggaling sa data using nung year 1790, 1850, and 1910. Kasi ang problema ko rito, ito si P of T, hindi ko alam kung ano yung ipla-plug in na value ng T para makuha yung population nung 1790. And I guess here, looking at the numbers, it seems that para makuha yung population kay 1790, kailangan yung i-plug in yung 1790. Alright? But this is my hunch. Alright? So, depende dun sa itsura ng population function. But you can verify this before doing the actual calculations or before doing the actual exercise. Pwede nyo i-verify. Compute nyo yung P of 1790. Plug in nyo yung 1790 dito. You'll get a number. And then check if that population value is near to the actual population of the US in 1790. Kasi inisip ko nung isang araw, baka naman ang kailangan ko ay P of 0 o kaya P of 1 para makuha yung population ng 1790. Pero it looks like 1790 dapat kong i-plug in para makuha yung population ng 1790. Alright? So paki-double check na lang para medyo masanay din kayo ng data verification. And then in A, you will implement the formula you derived in number 1 using you by to estimate the yearly growth rate from 1790 to 1910. So gagawa kayo dito ng table 1790, 1791, 1792 hanggang 1890 hanggang 1910. Kaya sabi gumamit daw ng step size h equals 1 tapos yearly growth rate. So mako-compute nyo si P of T, right? Using yung formula na binigay dun sa model. So mako-compute nyo yung laman nito. Tapos i-approximate nyo daw yung P prime of T. Sa lahat ng dates na to o years na to using the formula you obtained in number 1. Kaya lang, si number 1, 4-point backward formula yung hinihingi. So, ibig sabihin, halimbawa, para makuha yung approximate derivative kay 1790, kailangan nyo yung tatlong previous values. So, posible pala na kailanganin nyo yung P of T para kay 1789, 1788, at saka 1787. Kailangan mo yung function values kasi etong apat na to yung gagamitin natin para ma-compute yung approximation para kay P prime of 1790. Alright? So, bakante nyo na lang yung 1787 hanggang 1789 na derivative. Kasi ang sabi lang naman dun sa problem ay growth rate mula 1790 hanggang 1910. Okay? Via a year. So, kukomputing ko yung P prime of 1790 hanggang P prime of 1910. Right? Estimate natin yan. So, yun yung first step. Then, in the second step, or then the second problem, we will perturb the p-values of a number of order 10 to the fourth. So, ibig sabihin, uulitin ko lang yung proseso, pero ngayon, yung data kunwari ay tainted by some measurement error. So, kunwari yung data ay p prime of t. Now, anong gagawin nyo rito? So, ang gagawin nyo lang ay bawat isang population value, dadagdagan nyo lang ng isang random number. So ito ay P of 1787 plus random number 1, P of 1788 plus random number 2, hanggang P of 1910 plus random number of, say, capital N. Ayoko lang bilangin kung pang ilan na siya. Tapos, itong mga random numbers na ilalagay nyo, dapat order 10 to the fourth. So, dapat ang itsura nila ay something times 10 to the fourth. So, ibig sabihin, you can choose the random numbers from the interval negative 10 to the fifth hanggang 10 to the fifth. So, piliin nyo yung mga random numbers na papang-perturb nyo dun sa actual data on the interval negative 10 to the fifth hanggang 10 to the fifth. Okay? Now, baka magtaka kayo, sir, bakit ang laki ng perturbation? Di ba ang usapan natin, yung perturbation ay maliit na value lamang. Well, the population values are in millions. So, yung mga population numbers na to ay mga millions. So, pag pinerturb natin by around thousands, yung population values, hindi pa rin ganun kalakihan yung relative difference. Pag kinuha niyo yung relative difference nito, minus that, divided by the actual population, it will just be some percent. Okay? Or a fraction of a percent. So kaya pwedeng yung perturbation talaga order 10 to the fourth. And then ulitin nyo lang yung evaluation process para kay P prime para makuha nyo yung estimate annual growth rate using perturbed data. Okay? So yun yung sa part B. Then sa part C, gagamitin nyo itong table na to at saka itong table na to, but this time in a Richardson extrapolation procedure. Luckily, ito yung sabi ko na swerte pala kayo. Hindi nyo kailangang i-redo yung Richardson extrapolation. Bakit? Kasi yung formula natin dito ay order 2. Dahil order 2 na siya, pwede nyong gamitin yung Richardson extrapolation na nakuha nating formula dito. Okay? Kasi ito nga ay nag-work para sa kahit anong formula of order 2. Luckily, ang pinaderive sa inyo sa part 1 ay formula of order 2. So kailangan nyo lang gamitin yung Richardson extrapolation formula na dinerive natin kanina para masagot si part C. Both using the actual data and the perturbed data. And I think that's it. That would be your lab exer for Monday. Okay. So if you have more questions about it, please ask your lab instructors. Seek their guidance if needed. All right. So and that would be your task for your 3 hours on Monday. Okay. But let's see. Do I forget? Did I forget anything? I don't think so. All right. Do you guys have any questions or clarifications? Parang may gusto akong sabihin pero nakalimutan ko. Let's see. Okay, never mind. Mukhang hindi siya ganun ka-importante. So, do you guys have any questions? None? All right, then thank you for joining me this early morning. Enjoy the rest of the day and enjoy your weekend. And as always, let's see each other again on Wednesday. Bye, guys.
Thank you
Thank you
po.
po.
All right.